moving a little bit ahead and talking about turbulent combustion. So, first question is, why do we need to study turbulent combustion? Laminar combustion is not good enough. So, what are your thoughts on it? Whether laminar is end of the story, or we need turbulent, or why we need turbulent?
In real
Anybody?
life, we have more examples of turbulent combustion.
Yes, I will add to that. I will say that most of the real life application, except for your simple Bunsen burner or your LPG stove in your home, most of the devices which run on combustion, they rely on turbulent combustion. Okay, this is a matter of fact. And okay, to understand the basics, we need to start with laminar flow. That is true. But when you go to turbulent combustion, there are a lot of characteristics, flame characteristics, or the way it reacts, or the way we model it. They are so different from laminar flame that it becomes a separate topic in itself. Okay, turbulent combustion it is in fact a very hot area of research. And how do you understand or model what goes on in a actual engine, what goes on in a gas turbine or IC engine? This is what we are going to understand. So let me start with one slide from Professor Chaudhary. So what is showing here is these are spherically expanding flame. I take a big vessel, I fill it with some fuel, and I just burn it. But as you can see, there are three different phases or three different. His statement was three phases. Phase means your phase. Three phases of combustion. So can anyone define what are the three different aspects or three personalities of flame? What you can see here. What is the first one?
Initiation.
No, no, no. Let us say these are three different cases, not the same case. Three different types of flame.
Sir,
What?
can you repeat the question? I cannot understand
Turbulent,
what the question is.
semi-turbulent, मतलब laminar,
Yes, yes, yes.
semi-turbulent and
So
turbulent.
my question is, three different types of flame are visible here. So what are the three different types? First one is what you have already studied. What is
So
that?
laminar,
Laminar flame. This looks nice, smooth sphere, no wrinkles. It is nicely going out. Laminar flame. But this is a very ideal scenario. Most of the cases you'll have something like this or this. So this is it is highly turbulent case. This is you can see some cells are starting to develop. You can see some cell-like structure, right? You can see or cannot see.
yes sir.
Okay, so these are called cellular instabilities. I spent 2 years just to get some understanding what is going on, and I still don't know a lot of things. So this is a lot of a very interesting area of flame phenomenology, and where we also talk about fractal nature of this flame flood. I will show you some videos maybe. Okay, let us look at this video. So in that you see that initially the flame is small and nice, but as it grows, okay, it starts to, let me pause it somewhere. So this video I got from FM Global Experiments. So these were actually my collaborators. I got a lot of data from them for about these experiments actually. So now can you see those cellular structures?
Yes, sir.
Is it more clear? So these are called, this is because of cellular instability. Okay, this happened, I think this is from an example from propane. The same thing happens if you use at a larger radius for methane, at a smaller radius for hydrogen. But most of the cases it happens. I will not be going into the detail of the formation, but it is one of the most interesting process, and After a certain time, it will become turbulent. There is something called flame generated turbulence. Okay, let me look at one video. Yeah. So this is what happens. Now let us see an application where that happens. This spherical expansion that you see. Now, if you remember the last example we talked about in the limit phenomena, last chapter, what was the last example? Just now we discussed. Anyone?
Sir, we check flammability
Yes, flammability in what? What was the application? What was the
in a kitchen.
in a kitchen or any room? So basically, if you fill gas in a room, this is what is going to happen. So in that example, it was beyond the flammability limit. Suppose if you are able to create a mixture which is within the flammability limits, okay, like this, then what will happen? It will, and if you, in this example, what we are doing is we are filling a big room with gas and we are putting ignition at the center of the room. Okay, so you see a nice spherical type of flame coming out. Let us look at what happens in practice. So let us say this is what we're talking about. There are some cylinders. Okay, these are gas cylinders. They leak out. They leak, and this is the room. They fill that room. Is it okay? Now I burn it from one side, or I put ignition somewhere. So let's see what happens. Have you seen that? And let me tell you, this container what you're looking at, these are shipping. These are standard shipping containers. Okay, and this wall is thick metal wall. You need a big hammer to make such type of deformation. Oh, interestingly, what you see here, this is a door. This is a metal door. It was so heavy that one person cannot lift it alone. Two people have to lift it from both the sides. Now see how it is flying. So we'll look at that in time resolved images. Okay, take a closer look. I think. Okay, anyone can tell me why this image is going up and down? You see some
Sir, vibrations due to the explosion, maybe.
yes, actually the camera was also shaking a little bit. Imagine the type of blast what we had. Now this will be more interesting. So this is explosion. A lot of it is turbulent, and this is the end effect. You see the door dancing. I have lot of videos. Like, let me look at another video. So this is
Sir, what was the purpose of this experiment?
so we are trying to see if suppose that accident happens in some factory, if gas leaks and it explodes like this. So we assembled different configurations and we measured how much pressure will be generated. What is the peak pressure? If you look at the initial slide, somewhere that information is there. Okay, this is P stat. What was the initial pressure? And this is the area of the vent, the area of the door. Okay, and okay, this is hydrogen. So 24% volume of hydrogen was filled in this container, or let us say the room, and this is the area of vent. So what do we do is, when we have this type of application in an industry, or suppose this happens in your home, so what do you want to be safe, right? So if it is a closed room, this is what is going to happen. It will, every wall will explode. So to prevent that, to keep you safe, what we do is we provide some vent. Let me show you a vent video actually. Okay. So you saw the last video, right? You don't want that to happen with anyone. So what you will do is,
Sir, in that process, what was the value of peak pressure?
wait. Let me pause it. Yeah, tell me. What is the question?
Sir, after that process, what's the value of peak pressure? As you
Peak
said,
pressure
something
was
of,
something
yeah,
about 1.5, 1 to 1.5 bar.
1 to 1.5 bar. And
Oh,
what was P stat?
P stat was for that initially you have went. I will show you this. P static is for initially what was the pressure or what is the pressure at which. Okay, let me finish that video, then I will be able to explain.
Okay.
Okay, so okay, let me first talk about the why that vent is required at all. So what do we do is last video. I hope you no one wants that to happen, right? I don't want this to blow up. All the walls should be broken and all that. So what do I do? What is I want to keep it little bit safe. So any idea from anyone how to make it safe? See, if there are you're using gas, it is going to leak. Let us assume we need to install mechanism that it does not leaks, but let us say that it leaks. If that happens, let us say if it leaks and if it gets ignited also. Usually, when you talk about safety, I will install gas sensors that if it leaks, immediately I should get a signal, or let us say electricity should be stopped so that there is no spark or burning. Most of this burning happen because you have some electrical connection and there is a spark. When you read newspapers about gas leakage, you will always most of the times you will hear that there was some short circuit. Anyone remembers that?
Yes, sir.
That LPG leakage is there because of short circuit. There was fire. So most of the cases it happens because of an electrical wiring. Okay. So to prevent that, okay, so we can do some safety measures to prevent leakage, to prevent short circuit and all that. But let us say worst case, if it happens, you tried a lot, but still gas got leaked and it exploded. Okay, let us generally as an engineer, you first thing to consider is the worst case scenario. When you design a bridge, you talk about the maximum load and then you take some factor of safety, right?
Yes, sir.
Similarly, let us say I'm talking about the worst case that gas leaks, it burns and it explodes. But I want to keep this building or this container safe. So what can I do? Any idea? Even if it is exploding, I don't want the walls to break.
सर पीक प्रेशर से ज़्यादा हम वो प्रेशर को वॉल वैसा डिजाइन करें कि वो
Okay,
टूटे ना.
that is also a good approach. That wall should be stronger than the peak pressure to withstand the peak pressure. That is correct. Other than that, now let us say I have some instruments inside, some equipment inside, which will anyway break. Okay, wall will not break, but that will break. Now what?
Sir, we can make a way uh,
You can?
to the gases. Means after the combustion, there will whatever the gas we can make a passage for them, which
Yes,
will
yes.
break open after some critical pressure. And
Yes.
in this way, as the gases get out of the container, the pressure will be reduced and the extent of damage will be reduced.
Have you read it somewhere or you are just guessing?
No, sir. Sir,
Your
I have
guess
seen
is
some.
uh, your
Uh,
guess is exactly correct. That's why I am curious. That is one very effective strategy to contain reduce pressure. That I will show you in this video. But I am quite surprised. You exactly guessed what I am going to show. So let us see. So this is the pressure relief. Generally, we have something called vent panel. For the experiment, we just put these are plastic sheets, as you can see. You can see these sheets. So these are thick plastic sheet. It is not like your shopping bag type of plastic. This is like little thick, but it will explode. It will burn. So what we are doing here is we are providing a weak linkage. This is a weak part of your system. So I don't want the walls to break, but this will break, this will open, and this will allow the gas to go out, as you can see here. And as you will see, the walls of the container now safe, and the peak pressure generated will be much lower than that. This is a little dark video. I can show. Okay, so you can see there's some deformation, but it is much lower than what you saw in the first video, right? Let me show you some video where there's some light also. Why this is not closing? Okay, now let us look at this one. Okay, one more video was there which I wanted to show you. This is the vent panel what I'm talking about. Okay, let us play. This is actually done by a company called Jexcon. Okay, now these are the vent panels what I talked about. So what we do is basically when we install, we give some. These are designed for a fixed pressure. Okay, someone was asking P stat. What is a P stat? If you remember, who was asking that?
Yes, sir. I was asking.
Okay, now I will answer the question. So P stat is the pressure when this vent panel will open. Okay, we give some pressure setting for this to open. Let us watch that in a slow motion. Okay, these are the vent panels. Okay, on the top of the roof, you can have a window at the side on the door or on the top. Okay, now this you will see this opening. See, all are exactly opening at the same time. Why? Because they are so precise. They work exactly on the same pressure. If you look at this particular image, so they open, they release, most of the gas is thrown out. That is why the inside pressure, what is developed inside, is much lower from a closed case. See, now camera is also shaking a bit. One more snapshot. Yeah, a different view is there. Okay, one interesting question about hydrogen. So we had hydrogen here. If hydrogen leaks, if let us say, forget about burning. If let us say, okay, so let us say, let me stop it here. So let us say this is a room. This is a room, or you can see my mouse pointer, right?
Yes, sir.
Okay.
Yes, sir.
So this is a room I'm talking about, and let us say some equipment. Forget about this. Let us say from one corner I leaked some hydrogen. So what will happen? Hydrogen will go mix uniformly, or it will be settled down, or it will go up. What will happen?
It will go up as it is light.
Okay, very good. So if you look, if you don't do anything, generally what we do is we put fan and we mix it thoroughly, or we have different for this experiments. What I'm doing here, we mixed it and make it sure that oxygen hydrogen is thoroughly mixed. Okay, if you don't do that, if you leave it undisturbed, you allow it to settle, hydrogen will stratify. Okay, what do you mean by stratification is that concentration will not be uniform. If I take a probe here and I measure hydrogen concentration, that will be higher. If I take a probe here, that will be lower. So hydrogen is basically, it will let me take a screenshot and explain to you. Okay, so if I have a vessel here and if I measure hydrogen concentration, it will be high here, it will be low here. So generally we have some distribution. Hydrogen is, let us say, 20% here, 5% here. So the quantity of hydrogen goes on increasing. This is what we call as stratified mixture, or mixture whose distribution is not uniform. Is this clear to everyone? Yes, no, or what?
Yes, sir.
So this
Yes,
is a
sir.
very peculiar behavior of hydrogen. Other gases are also, if the density is different from air, it will have some effect. But hydrogen is very very light, so it will definitely form a stratified mixture. Okay, and different at different levels, it will have different flame velocity and so on and so forth. Okay, so how much time we have left? So we have 5 more minutes. Should we stop or? Okay, let us stop for today. Tomorrow we'll try to cover this turbulent flame. Okay, any questions so far?